That's great. Thanks. So the objective of this work was to assess how the North Pacific storm tracks have changed in recent decades. And this was done with Yanni Yuval, who is currently working at Google. And I'll start with just a brief motivation of why we should care about mid-latitude storms. It's probably trivial, but we care about them because they affect us on both short weather timescales and also on long climatic timescales. So on the upper panel, on the upper part of this slide, you see this schematic of how the upper level flow is strongly linked to weather system and the surface. And on day-to-day timescale, this kind of storm track structure affects, of course, our winds, variability, temperature, and precipitation. On longer timescales, and these are the timescales that I'm going to focus on this talk, when talking about multi-decades, for example, these mid-latitude storm tracks account for most of the heat, moisture, and also momentum transport across the mid-latitudes. And to illustrate this, I'm showing in the bottom right, this plot is taken from Hartmann's book. You see the total northward transport of moisture in the atmosphere. So basically what they did, they took, this is the climatology from ERA interim, and they vertically integrate the northward transport of moisture and also zonally, so they plot it as a function of latitude. This is the black line here. And then they decompose.
Ray, we can't see the slide. Have you moved the slide on?
Oh.
Yeah, that's it.
Now you see my slide?
Yeah. Thank you.
Okay. Okay, so let's again focus on the plot on the bottom right. Again, you see this is the climatology of the northward transport of moisture in the atmosphere. Okay, so this is the black line. It's plotted as a function of latitude. And then they decompose this black line to the what the mean flow is doing in the atmosphere in blue versus what mid-latitude eddies are doing in red, or storm tracks. And you can see that in the mid-latitudes, the eddies contribute the most to this poleward transport. It's positive in the northern hemisphere and negative in the southern hemisphere. And I will touch based on the impact specifically over the North Pacific towards the end of the talk. Okay, so let's start with what models project would happen to the mid-latitude storm tracks in the North Pacific. So this is taken from CMIP 6, and we examine the storm track intensity by looking at their eddy kinetic energy. This is a canonical metric for storm track intensity. And the eddy kinetic energy is basically you can see at the bottom left here, you take the winds, you subtract some time mean, and then you get a deviation from time mean. And if you take the square of that, you will get the kinetic energy of the eddies, basically. So this is what's plotted here. The black contours are this is the climatology of the storm tracks. And you can see that it lies, of course, above the Pacific, and the downstream regions affect the west coast of the US and Canada. And in colors, you see the projected changes based on CMIP. So these are basically the difference in this EKE metric between the late 21st and late 20th century. So red color showing us regions where the storm tracks are projected to intensify, and blue where they're expected to weaken. And you can see that they form this kind of dipole behavior, intensifying at higher latitudes, weakening at lower latitudes, which suggests a poleward shift of the storms, right? It's going to push this entire distribution polewards by the end of the century. And this, of course, is going to have important impact both over ocean, but also over land. And just one example over land, this is taken from Salafi 2006. You see here the future changes in precipitation based on CMIP 3 models over the West Coast. And you can see this, again, dipole behavior. You see the increase at higher latitudes and the decrease in precip in lower latitudes. And they attributed this changes in precipitation pattern to this shift in the storm tracks. Now, what we're trying to understand is whether this poleward shift that we see in the projection already emerged in recent decades, and we are not the first to try to ask this question. One example is taken from Wang et al. 2016. This is the historical changes in reanalysis, ERA interim. It's basically the difference between two periods over the entire historical period. Again, they're looking at this EKE, this eddy kinetic energy metric. And you can see over the Pacific region already this poleward shift pattern, right? You see the intensification at higher latitudes and a reduction at lower latitudes. So it seems that in reanalysis, at least, we're starting to see this poleward shift. So let's start by quantifying this poleward shift. And to quantify this, what we did is we basically took each winter, we estimated the storm track position, the latitude of that, and then we had a time series of the latitudinal position of the storm tracks each winter over the historical period, and we basically did a linear regression of that. So we have a trend of the positions. So this is what you see here. This is over the 1979 to 2024 period. In the bars here, you can see the distribution of the storm track position trends. This is in latitudinal degrees per year. Blue is from CMIP 5, gray is from CMIP 6, and you can see that some models show positive values, meaning a poleward shift in recent decades. Some show negative values, meaning an equator shift. So there is no robust signal in the models. In contrast, in reanalysis, this is the vertical red line, which is the mean of 5 different reanalyses here. We have ERA5, NCEP2, MERA2, GRA3Q, and CFSR. And the shading is the range across the reanalysis. Reanalysis show a very strong poleward shift that is not captured by the models. In fact, not a single model that we analyzed here, we analyzed something like 40-something models, is able to capture the poleward shift that we see in reanalysis. And this discrepancy between models and reanalysis, it basically leads to large uncertainty in how the storm tracks have changed, because we don't know which one is right and which one is wrong, because both could have biases when we look at multi-decadal changes. For example, both are based on models, right? Even the reanalysis. So if they are not adequately representing, for example, subgrid processes that are important for the storms, then they could have biases when you look at long-term trends. Also in reanalysis, because the assimilation procedure uses different data sets throughout time, then it could also make some artificial trends when you look at long-term trends in circulation. And this uncertainty eventually basically prevents us from assessing the role of climate change in setting the storm track position in recent decades. And most importantly, we don't know how confident we are in model projections, because we don't know if the models are doing a good job or bad job in capturing the historical changes. If they're doing a good job in capturing the historical changes, then we have more confidence in their projections. If they're doing a bad job, then we have less confidence. And all of that together led the latest IPCC report to conclude that there's only medium confidence in the historical shift that we see in reanalysis here, in spite of the robust signal, and that the projected shift that I showed you earlier is only more likely than not. So to reduce this uncertainty, increase our confidence in how the storm tracks have changed in recent decades, what we need is an observed wind record that is continuous in time and space that would allow us to calculate the storm track's position. Unfortunately, there's no such wind record available, especially not over the ocean where the storm tracks mostly lie. But there are good measurements at the surface, right? We have good measurements of surface temperature, for example, and surface pressure. So what we did next is we derived an observation-based proxy for the storm tracks. Basically, we want to link our eddy kinetic energy, right? It's a vertically integrated eddy metric to some surface variable that we have observation of, and use that as a proxy for the storms. That's the idea of what we want to do. I'm not going to go through the derivation because I don't have time, but I do want to show you how we got to what we got. So basically, we started from it's a 2-layer quasi-geostrophic model. Doesn't matter if you are aware of this model or its equation. This is a good starting point, because if you look at the momentum equations in the model and you vertically integrate them, you get a balance between the vertically integrated eddy momentum fluxes and surface winds. And this is a good starting point because this is eventually what we want to get. We want to get a link between the vertically integrated, in our case, storm track intensity or eddy kinetic energy, and some surface variable. So to get an estimate for the surface winds, we use the meridional momentum equation that near the surface, it reduces to a frictional geostrophic balance between the Coriolis force, pressure gradient, and friction force. And if you combine these two equations together with the fact that near the surface there is a balance between the meridional and zonal velocities, what you get is that your vertically integrated eddy momentum flux convergence is linearly related to sea level pressure gradient. And since these eddy momentum fluxes play a key role in transferring energy between the eddies and the mean flow, from that we can also suggest that our storm track intensity, and this is what I want you to take from this slide, you can ignore all of this derivation, is that the vertically integrated eddy kinetic energy, the storm track metrics, should be linearly related to the meridional gradient of sea level pressure. And there are available measurements of sea level pressure. So if this link actually holds, and we can verify this in models and in reanalysis, then we can take measurements of sea level pressure, estimate this gradient on the right-hand side, and use it as a proxy to constrain the left-hand side. Okay, that's the idea of what we want to do here. Right, so let's start by seeing if this link actually holds, and we can start by looking at the models. So what you see here is the time evolution of, on the left y-axis, is the position of the stormflex relative to some reference period. So it starts around 0, and for that you need to look at the black line, which you can barely see. That's part of the point, but it's just below the blue line. There's the black line that corresponds to the left y-axis, and it shows that the model, this is the CMIP mean, show you a poleward shift of approximately maybe 2 to 3 degrees by the end of the century. And the blue line, which corresponds to the right y-axis, is basically this gradient of sea level pressure that we argue that is linearly related to the EKE. And you can see that it nicely captures not only the overall poleward shift by the end of the century, but also the interannual variation in the stormflex position. So it seems that this relationship that we found nicely holds in the CMIP mean. To show you that it also works across the models, we examined the historical changes in those two metrics, and this is the panel on the right. So the y-axis show you the historical trends in degrees per year in the stormflex position, and it is plotted against the historical trends in this sea level pressure gradient metric. Okay, again, across models. So each symbol here is a different climate model. And you can see there is a nice overall linear relationship between those two metrics as we expected from this balance. And the black arrow bar on the y-axis here basically show you the mean value of the CMIP and the 5 to 95 range here, percentiles. And the x-axis value of this arrow bar is meaningless. It's just to show you how these dots are distributed along the y-axis. So now we can take measurements of sea level pressure, calculate this gradient, calculate the trend, and add that to the x-axis here, right? And specifically, we used the ICOEDS dataset for sea level pressure, which collects millions of sea level pressure measurements per year from ships, buoys, coastal stations. So we did that, and this is the green arrow bar. Again, it shows you the value of the observation on the x-axis. Its y-axis value is meaningless. And basically what we do here is an emergent constraint analysis. We leverage the fact that we found a strong linear relationship between those two metrics, that it has a physical meaning, right? It's come from the momentum equation. And then we basically project the observation onto this linear relationship to get a constraint on the y-axis. And this is the purple arrow bar that you see here. So it suggests a mean observed value of 0.1 degrees per year shift. You can see that only 2 models out of the 40-something models analyzed here are able to capture the observed trend, and most models actually lies even below the uncertainty of the observation-based constraints. So this suggests that the projected shift that we saw earlier in models might be larger than the 2 degrees currently predicted, because it seems that most models seem to underestimate the historical shift based on observation. We can also add reanalysis to this plot. That will be the red arrow bar, and you can see that it sits nicely within the observation-based constraint. So regarding the discrepancy that we saw earlier, it seems that the reanalysis captured the correct magnitude of trend. Models seem to underestimate the degree of poleward shift in recent decades. So now we want to ask, can we attribute this poleward shift to climate change, to external forcing, or is it due only to internal variability? So to answer this question, we did a detection analysis. Basically, we took a signal to noise ratio approach. The signal is the stormflex position trends over the historical period. And the noise is one standard deviation of all trends with the same signal length, but they stem only from internal variability. So we basically took pre-industrial control runs, and we estimated how these trends in the stormflex vary only due to internal variability, and one standard deviation of that will be our noise. So the signal, we basically say it's detected when it exceeds 2 standard deviation of that internal variability, meaning a signal-to-noise ratio larger than 2. When it exceeded that, we can say that it's very unlikely that internal variability alone could explain the trend that we see in the observation. So let's do the analysis. First, we're looking at the observation here. You see that the observation shows a signal-to-noise ratio of 3. So above the threshold here that you see the horizontal black line of signal-to-noise ratio of 2, meaning that the signal has emerged in the observation, and we can attribute this to external forcing. In contrast, when you look at CMIP models, you can see that the mean signal-to-noise ratio is very low, consistent with the fact that models seem to underestimate the poleward shift in recent decades. They also underestimate the emergence of the signal, which again suggests that they underpredict future force changes in the stormtext. Interestingly, if you also look at AMIP runs, which prescribe observed SST and sea ice in the models, still, even if you take the observed SST, we don't adequately capture the emergence of the signal, suggesting that SST biases in models might not be the main reason for this discrepancy between observations and models. And lastly, I want to discuss one impact. I mentioned in the beginning that one climatic impact of the stormtext is affecting our heat and moisture fluxes in the mid-latitude. So to see that, I'm showing here the historical trends in eddy heat flux on the left and eddy moisture flux on the right. Again, this is taken from the reanalysis. And what I want you to take from this plot is two things. First, you can see that the poleward shift signal is also already evident over land. You can see positive values in both of these at high latitudes, negative values at low latitude. So we already see this kind of poleward shift movement. And this pattern would act to warm southwest US, would act to cool and dry northwest US and British Columbia, and would act to warm and wet Alaska. And within these black contours, you basically see regions where less than 10% of the models capture these trends. So you can see that models not only underestimate the poleward shift of the stormtext, but they also underestimate the patterns of heat and moisture flux trends over the west coast of North America. All right, I'll conclude. I'll say that I show you there is a discrepancy between models and reanalysis regarding the rate of the shifting stormtext in the North Pacific towards the pole. And to overcome that, we basically derived an observation-based proxy for the stormtext based on sea level pressure. And then we took measurements of that, and we showed that the stormtext have shifted poleward consistent with reanalysis, but the rate is underestimated in models, and we're able to attribute this to climate change, to external forcing. I showed you also that this poleward shift is also evident over land when you look at the heat and moisture fluxes, and models, the fact that they are underestimating this poleward shift and the impact over land might suggest that the projected changes might be larger than current predictions. And if you like to read more, you're more than welcome to check our paper.